Okay.
Is that for a log?
Okay. Now I'm recording. All right. Let me start this over. This is the Math 112B midterm exam review. We have a packet that I have distributed to you guys here in the classroom. And for those joining by eCampus, I have dropped it into the chat. So just look for it to show up in the chat. If you're having any trouble getting that to show up, you can email me at lisa.blue@eku.edu and I can email it to you that way. And what we're going to do tonight is we're going to use these student learning outcomes to guide our practice on these problems. And so the student learning outcomes, I really like organizing our reviews according to these outcomes because they follow this Bloom's taxonomy, where at the lowest level of being able to talk about something is to say, hey, do you remember what the compound interest formula is? Can you write that out for me? Do you understand how to solve for one of the variables in the compound interest formula? Can you use what we know about logarithms to describe the Richter scale? All right. And then can you analyze this equation? So say we're graphing 12 to the, or say y equals e to the 12th, something like that. Can you analyze that information and tell us what that e function is doing? What does it make the graph look like? You usually won't get any higher than evaluate when it comes to an exam. Create, this is more like a capstone or a portfolio course type situation, but definitely these lower levels are all fair game. Usually the remember is implicitly tested over by, hey, do you know how to use a formula to solve this? All right. So using this to our advantage, you want to look at these learning outcomes and these questions, make sure, do I understand all the terms? If they're saying amortize the mortgage, I don't know about you guys, but I go a little cross-eyed. Okay, amortize, what does that even mean? I know it's an English word, but that's about it. So make sure you understand the terms. You understand what the question is asking you to do. If you understand what the question is asking you to do, then you cut out all the fluff that doesn't need to be there and focus on just the numbers and units or what have you to solve the problem. All right, what I've done for you in this packet is to find examples of these questions so that we can practice and say, yeah, do I know how to do every aspect of this learning outcome? You want to make sure you know how to answer the question. And then do you know how to check your work? So for example, if you've got, you've solved for 2 roots of a quadratic equation, can you plug those back in and verify that those are valid answers for the equation? All right. So if you say no to any of those questions, you know to go back and focus your efforts wherever that may be. All right. So for the midterm, your instructors are covering all of chapter 4 and all of chapter 5. Now, we have these algebra toolbox sections. And while we're not testing over these explicitly, you're not going to have exam questions directly out of this toolbox. It's expected that you understand how to work questions from the toolbox sections. All right, so I've included those in our review. So you can see here, chapter 4, algebra toolbox, that is on page 3. And I've written learning outcomes, but also textbook notes. So you can see here that I've got notes from the textbook over linear functions, everything you need to know about linear functions or quadratic functions. All right, so I was trying to make a study guide, cheat sheet, extra practice all in one in this very robust packet. Okay. So with that, I'm going to turn the session over to our very capable math CECs. Yep. And I want you all to peruse the packet. And if you see something you'd like to see worked, then either speak it out, drop it in the chat, whatever works for you. Let us know you want to see it, okay?
All right, my name's Maddie. I'm a CEC and a tutor for the math department, and I'm going to be going over chapter 4 with you guys. So the first learning outcome that we have is graph related functions and describe the transformations used to obtain one from another. Do you guys have any questions or want to go over any of the examples in this section? In the chat.
See.
Nobody has any question?
Can we go over 12?
12? Absolutely. Did somebody say another one?
22.
22, okay. Okay, remind me of 22 when we get down to that page and we go over that. All right, so for number 12. We have y equals 1 over x and y equals 2 over x minus 1. All right, so first we can look at this x minus 1 down here. We see that there's that minus 1. And anytime that we have a number either added or subtracted from the x, we know that there is going to be a horizontal shift. So since we have that minus 1, it is actually going to go the opposite way. So instead of towards the negative direction, it's actually going to go to the positive direction. So it's going to be a horizontal shift to the right. So stop it. On both sides. Okay. So we're gonna have, this is y equals 1 over x.
Oh.
Okay, so like I said, we're gonna have a horizontal shift to the right of 1 unit. And then we also have this 2 up here, which means we are going to have a stretch by 2 units. So since it's a 2, it's greater than 1. We know that this graph is going to be steeper than the original 1 over x. So instead of splitting the graph at the y-axis, we're actually going to split the graph at x equals 1, which means we're just going to have a steeper graph 1 unit to the right. Does that make sense? Any questions about that? All right. Any others that you want to go over?
I don't know if there's a lot of actors, but one of the things I've kind of had trouble with telling the difference between a vertical compression or stretch and a horizontal compression or stretch.
Just give it a way to explain that.
So the stretch, so the compression and stretch is based on what the actual term is. So if we were to use a term larger than 1, it's going to make our graph compress and go up larger or faster. So it's going to compress it. But if it's less than 1, it's going to take a wider time. So it's going to stretch it. So it's less vertical and horizontal and just more stretch and compress when multiplying.
But my thing is, I don't understand how to tell the difference between those two. Sometimes it'll be a horizontal stretch, sometimes it'll be a vertical stretch. How do I tell the difference between those two? Like whether it's a horizontal one or a vertical one?
The stretch or shift?
Stretch.
I think it's later in the packet. I think we've got some information on that later in the packet.
We did have requests for 13 and for 10.
For 13 and 10.
Yeah.
Okay.
It's the scariest.
I was gonna say, so I would say we can go over 10. All right. So we're gonna go over 10. And if you want to see 13, we can look at it later. You can come by the tutoring center. We can get some extra help. Or we can come back to it later if we have time. So for 10, we're given y equals the square root of x. And then y equals negative square root of x minus 2. So in this one, the original graph is going to look something like this. And in the second equation, we have two transformations. We have this minus 2 and we have this negative. So we know that because there's going to be, because of the negative, we know that there's going to be a reflection over the x-axis. So that's going to make it negative. So instead of going this way, it is going to be reflected over the x-axis. And then we also have this transformation of the minus 2. And so since it's with the x, we know that that's going to be a horizontal shift. And instead of to the negative direction, it's going to go the opposite way. So it's going to go to the positive direction 2 units. So it will look something like that. Any questions about that?
I would like to add on these. You can also use your calculator to kind of see what has happened to the graph. And that could also help.
So here's some more information about transformations and symmetry with respect to the y-axis, the x-axis, and the origin. Do we have any questions about any of these problems? Did you say 22?
Yeah.
Do you still want to see 22?
You kind of just explained it.
Okay. Do you have any other questions about any of these examples?
In chapter 4, in general.
Just on this page,
20.
20. All right, suppose the graph of y equals x to the 3/2 power is shifted down 5 units and to the right 4 units. So we're given the base equation of y equals x to the 3/2. And we know we need it shifted down 5 units and to the right 4 units. So for the shift of down 5 units, we know that that's going to be a vertical shift. So that's going to be separate from the x. So we're going to have y equals x to the 3/2. Then down 5 units would be minus 5. And then we also have to the right 4 units, and that's going to be a horizontal shift, which means it's going to be contained within the x. So that'll be y equals, and then x. So to the right 4 units, that's the positive direction. So we're actually going to need to use the opposite sign. So that's going to be x minus 4 to the 3/2 and then minus 5. Any more questions from this section? You ready? Number 15. So f of x equals the absolute value of x. And then g of x equals 3 absolute value of x. So right here, we're going to have a stretch of 3 units. So we know that that is what the graph of the absolute value of x is going to look like. So with a stretch of 3 units, it's going to be steeper. So instead of going like over 1 up 1, it's actually going to go over 1 up 3. So it'll look like that. Does that make sense? All right.
We had somebody asking for 22.
22. Okay. y equals x to the 2/3 is compressed by a factor of 1/5, then shifted right 6 units. So we have a compression by a factor of 1/5. Y equals 1/5. 1/5 x to the 2/3. Then we also have shifted right 6 units. So a horizontal shift to the right will be in the positive direction. So that means that we need to subtract 6, and that'll be contained within x. So I'll let you guys write that down, and then we'll move on to the next section.
We will be sending out a recording of this afterwards and all the notes that they're writing on this document too.
So the next learning outcome, we have identify transformations from equations and write equations from given transformations.
So we had a question saying, also would the absolute value symbol be relevant on a calculator? You want to talk about that? Or?
So it would be, there is a way to use the absolute value on the calculator. If you need help with that, we can talk, you can come to the tutoring center and you can get more help with using a calculator.
The absolute value function should be somewhere under math. So if you wanted to use the absolute value function, you go to math. I believe you go to, let's see, yeah, math, and then over to num, and it's number 1, ABS. And once you click it, it'll give you your absolute value bars. And you can use that whether you're in y equals or wherever you're at on there. So it's math, over to num, and then number 1, which is absolute value.
Thank you. All right, so do we have any questions about 26 through 28?
27.
27. All right. So for 27, we suppose the graph of f of x equals the square root of x is reflected across the x-axis and shifted up 2 units. What is the equation of the new graph? So we're given f of x equals the square root of x, and we have a reflection over the x-axis and then a shift up 2 units. So first we can reflect it across the x-axis, and in order to do that, we will have a negative sign in front, and then a shift up 2 units that will be separate from the x, since it's a vertical shift, and that will just be +2. And then for verify the result graphically, you can plug both of those into your calculator and look at the transformations to see what it looks like. All right. So any questions about, we can go to the next learning outcome, write an equation of a transformed function from its graph. Which go,
I also have a question on number 28. We don't have to work it out, but the little, the 3, what does that mean?
that is the cube root of x. So
Yeah.
that's like the opposite of x to the 3rd.
Yeah, so like, what does that mean when we're like doing your transformations? Like, does that mean anything?
That's more of a base function. So I can show you what the graph of the cube root is. Would that help?
No, so would it mean like an extra shift or reflection or anything?
No.
No, okay.
Any questions about 29 through 32? All right, we can move on. So determine symmetry visually. So we didn't really talk much about symmetry yet, but do you guys want to go over anything from this section? Any of these examples? Do we have any questions about
33
symmetry?
Even,
33. So it is, so it does have symmetry across the y-axis. What'd you say that's even?
If it has symmetry across the y-axis, that means it's even. If it has symmetry across the origin, it would be odd. If it doesn't have any symmetry, it would be neither. We had a question about 34 in chat.
34, okay.
While you're writing that down, so symmetry with respect to the y-axis and to the origin, if you look at the notes on page 8, I've got those written down for you.
So for the graph of 34, we can see that there is symmetry with respect to y, since it's symmetrical. And then we also have symmetry across the x-axis.
Wouldn't that one just be not a function?
So you're correct, it's not a function, but just looking at the graph, we can still determine whether it has symmetry across the y-axis and the x-axis.
Gotcha.
So to that point, if there is symmetry across the x-axis, it will actually not be a function, because that would mean that there are points that would make it,
Vertical line test.
yeah, it wouldn't pass the vertical line test.
You look pretty broad.
Yeah, exactly.
How do you determine even, odd, or neither?
So, I'm sorry.
Oh, no, I was gonna ask a question.
Okay, so an even function means that it will have symmetry across the y-axis. So you can look at that graphically, or going back up to where it talks about this.
Yeah, it's on page 8, it's under the sticky
Yeah.
notes.
Yeah, it's under the sticky notes. Where were we at? So we know that if it has symmetry across the y-axis, f of negative x will equal f of x. And if it has symmetry across the x-axis, f of negative x will equal negative f of x.
So, my question is that, so I know that what you're saying about that, which one do you flip first? Do you do the X flip and then the Y flip for symmetry, or do you do the, because I know you're supposed to be like flipping in the head, like in symmetrical across the Y axis, flip it, like that. The origin, do I flip it across the Y and then the X, or do I flip it across the X and the Y?
For transformations,
Just for determining origin, like symmetry.
do you have a good way to explain that?
It's across the y equals x line. So you'll look for symmetry across the line where y is equal to x, and that's just that diagonal line on your graph. And so if you see like a mirror image across that diagonal line, that means it's symmetric across the origin. A good example of that is x cubed. If you look at that graph and then also put in y is equal to x, you should be able to see that it looks the exact same on both sides. It should be a mirror image on that line.
And then speaking to the odd and even functions, that's under the sticky note. If you have symmetry with respect to the y-axis, that's going to be an even function. But if you have symmetry with respect to the origin, that's going to be your odd function. All right, anything else on that page, or are we ready to move on?
All right. So the next learning outcome, we have determined symmetry using a table of ordered pairs. Do you guys need to look over that? Have any questions? All right, we can move on. Determine symmetry algebraically. Do we have any questions about those or need to go over any of those examples?
Forty-three.
43. All right, so we have y equals 6 over x. So from under the sticky notes, as I was talking about earlier, we know that an even function, or if it has symmetry over the y-axis, f of negative x will equal f of x. And then across the symmetry across the origin is, thank you.
Because that would make it an odd function.
Right. So if we plug in negative x for x, we can see that y will equal negative 6 over x, which will be the same as negative f of x, which means that we do have symmetry across the origin because it follows this.
We had a question about 46 as well.
46. Okay. You might have to hop in here for. All right, so we're given x squared minus y squared equals 25. So I'm going to solve for y first. And then I'm going to plug in negative x for x to see what we get. So we will have y equals negative, the square root of negative x squared minus 25. And with that square, we're actually just going to get x squared minus 25 again. So we know that f of negative x is just going to equal f of x, which means that we have symmetry across the y-axis. Okay.
I'm not actually, is there a way to algebraically show if it's symmetric across the x-axis?
I don't know right off the top of my head. I use
Um,
graphic.
So
Yeah,
for that question, we can notice that x squared minus y squared equals 25 is just going to be a circle. And so it's also going to be symmetric around our x-axis, which that is what you would do when confirming graphically.
solve for x and plug in negative y.
That would probably be the way to do it. but
Yeah,
Yeah. So that's one you would also want to confirm graphically.
Can you reduce it further to x minus 5?
Wait,
I mean, you wouldn't need to.
it would end up being x plus 5 times x minus 5.
Gotcha.
Do we have any other questions about these sections? Okay. So the next learning outcome that we have is solve applications involving transformations of graphs. Do you have any questions about this? Need to go over an example? All right. Answer questions involving transformation of functions. Do we have any questions about this section?
Community 57.
57?
Yeah.
All right. Using data from 2016 and projected to 2025, the US medical marijuana revenue in billions of dollars can be modeled by the function m of x equals 0.037 times the quantity of x minus 6 squared plus 0.652 times the quantity of x minus 6 plus 4.537. X is the number of years after 2010. So the graph of this function is a shifted graph of which basic function? So when we're looking right at the x, we notice that there is a -6 that is contained with the x. So with this -6, we know that there is a horizontal shift to the right 6 units. So for A, and then we know that the basic function. The m of x equals 0.137 x squared plus 0.652x plus 4.537. So for the basic function, would you say you could just put x squared, or would you still use the numbers?
Is it on A?
Yeah.
Is it shift graph of what basic function? Yeah, of just x squared.
Okay, and then we know that this is just a quadratic function. So the basic function, we could just put y equals x squared. Do you need to go over B and C?
So for B, you would just fill in 24 for X.
Mhm.
Okay. And then, yeah, I don't need to see.
Okay.
Thank you.
Do we have any more questions about 59? Okay, we can move on. Any questions about 61 or 62? 61.
Yeah, sorry. Go over 61. Awesome, thank you.
All right, so the monthly average cost of production X sofas is C of X equals 30,000 over X plus 150. Will the average cost function decrease or increase as the number of units produced increases? Okay, so first, we can look at the graph of this function, see it visually. And since we have a reciprocal function, we know that it will look something like this. And with the transformations, we know that there's a vertical shift of 150 and a stretch of 30,000. So it will look something like this. So will the average cost function decrease or increase as the number of units produced increases? So as X increases, so we're going to go this way. We see that on this side, we will be decreasing. And then on this side, we will also be decreasing. So as the number of units produced increases, we will be decreasing. Any questions about that? And then for B, what transformations of the graph of the reciprocal function give the graph of this function? So we have two transformations on this function. We have this stretch of 30,000 and then a plus 150. So that 30,000 stretch by a factor of 30,000 and a vertical shift up 150 units. Are there any other questions about 61 or 62?
In this case, would it be a horizontal stretch because it's next to the X?
Did we wait to answer that?
I don't
remember.
know. I
Vertical
don't
stretches.
think, I don't know the difference between vertical stretch and horizontal stretch. I just think that's stretch and
So-
compress, is it not?
I believe that
I'll get back with you on that one.
yeah,
I'm gonna Google it. Also, we have a question. If 30,000 were on the bottom, would it be compression?
so yeah, so that would mean that, so if we had 1 over 30,000 X, we could separate this into 1 over 30,000 times 1 over x. And since this is less than 1, it will be a compression.
So that's what I thought. So a vertical stretch and a horizontal stretch are the same as a stretch and a compression. So if your value, if your stretching factor is greater than 1, it's going to vertically stretch. And if it's less than 1, it'll horizontally stretch.
So compression is the same as a horizontal stretch.
It's on the, yeah, so it
Okay.
says it's applied to, the constant's just applied to the inside.
Okay.
Um,
Does that answer your question?
Yeah.
Okay. Do we have any other questions about 61 or 62? All right, we can move on. So find the sum, difference, product, or quotient of functions from their equations. So we're going to be looking at f minus g, f times g, f over g. Do we have any questions about this section, any of the examples?
All right, how about on the next page, the composite functions?
We would be looking at f of g and g of x. Do we have any questions about these examples? Need to go over anything? 18? Sure. All right, so we have f of x equals the absolute value of 4 minus x, and g of x equals 2x plus 1. So we're going to be finding f of g and g of x. So for f of g of x, which we can also write as f of g of x. So for f of g of x, instead of having this x, we are going to substitute this x for the g function. So we will now have 4 minus 2x plus 1 inside the absolute value, which we can simplify to 2x plus 3. No. Yes. Negative 2x. All right. And then for g of x, or g of f of x, we're going to be substituting this x for the f function. And we will have 2, it's the absolute value of 4 minus x plus 1. Do we have any other questions about this section?
Doesn't simplify any, it's just that answer.
I'm sorry.
Doesn't simplify any, it's just that answer.
Yeah, so since that absolute value, since there's stuff inside of that, we wouldn't want to simplify that any further because that would mess with the absolute value function.
How come the absolute value didn't carry over from the 2x plus 3?
On the f of g function,
Yeah.
so the g function doesn't have an
Oh.
absolute value. So when we input it into the f function, it'll already be inside of there.
No, I see what I ended up, and I thought that they both had an absolute value on them. Yeah,
Okay,
so I was looking at, I got you.
do you have any other questions? All right, so we can move on. Find compositions, sums, and quotients of functions from their graphs. Do we have any questions about these examples? We need to go over any of these questions?
Number 23.
23. All right. So we want to find f plus g of 2.
For the sake of time, go over A and D.
So we want to find f plus g of 2. So we can find f of 2 and g of 2 separately and add. So on this f function, f of 2 is 1. And g of 2 is negative 3. So f plus g of 2 equals -2. And then for D, f of g of 1 so first we need to find g of 1. And g of 1 is -2. So we will actually be finding f of -2 because we are substituting that -2 in for this g of x right here, or g of 1. And f of -2 is -3. So f of g of 1 is -3. So for this next section, solve applications involving function operations and composite functions. Do we have any questions about this section? All right. And then answer interactive figure questions involving the sum and difference of two functions. I believe that 32 or 52. Are there any questions about those examples?
Wait, can we go back up to 28? I'm sorry.
28.
Yeah.
Okay, so the total monthly revenue function for Easy Ride golf carts is given by R equals 26,600X. And the total monthly cost function for the carts is C equals 200,000 plus 4,600X plus 2X squared. So which function is quadratic and which is linear? So by looking at the functions, we have R equals 26,600X, and then we have C equals 200,000 plus 4,600X plus 2X squared. So we know that R is linear and C is the quadratic. And then form the profit function for the golf carts from these two functions. So the profit function would be revenue minus cost. So we want to look at the total amount that we would make minus the cost of what we would be spending. So we know that the profit function, which we can establish using P of X. So the profit would equal the revenue, so 26 X, and then minus the cost equation, which would be this really long equation. So that would be the profit function. And then CS is the profit function a linear function, a quadratic function, neither. And since we have this 2x squared, it would be a quadratic function.
Okay. So back on part B,
Mhm.
so you subtracted the two equations, right?
Right.
So how do you know how to subtract them?
So when we're looking at profit, we just know that we're going to be looking at the total revenue that we would make minus the cost of what it would take.
Okay.
So when we're doing profit, revenue, and cost, it's an intuitive thing, so you would just need to know. But if we were talking about another situation, it would probably explicitly say, like, you would subtract this equation from this equation.
I asked that because my professor gave us a midterm and there's a question similar. So
Okay.
I think where I'm going wrong on here is that I don't know like what profit equals
Okay,
revenue minus cost.
yeah. So just remember that when we're finding profit, it'll be revenue minus cost.
Okay.
All right. So the next section, answer interactive figure questions involving the sum and difference of two functions.
We didn't have any questions over those.
Okay. Answer questions involving the product / quotient of two functions. Are there any questions about that? All right. Inverse functions. So determine whether a function defined by a relation has an inverse, and if so, find the inverse. Are there any questions about 1 through 4? Okay. Determine whether two functions are inverses. Do we have any questions about 5 through 8?
Number 6.
Number 6, okay. So if f of x equals 4x minus 1 and g of x equals x plus 1 over 4, A, what are f of g of x and g of f of x? And B, what are f of x and g of x, are f of x and g of x inverse functions? So we're just gonna go over B since we already spent time going over composition functions. So 6 and then B are f of x and g of x inverse functions. So we're gonna look at f of x and g of x, find each of the inverses just to make sure that they are inverses of each other. So first we have y equals 3x. And in order to find an inverse, first,
That's number 5.
oh, thank you. That is my bad. So for 6, sorry, we have y equals 4x minus 1. And then we have y equals x plus 1 over 4. So we're going to look at the first equation first. And we're going to switch x and y. And then we're going to solve for y again. So plus 1 equals 4y, and then over 4. And y equals x plus 1 over 4, and we know that that is the inverse of 4x minus 1. And then we see over here that that is what we're given for the other equation. And so they are inverses. Are there any more questions about this section? All right. So evaluate functions and their inverse. Do we have any questions about 9 and 10? And then we can look at determine whether a function is one-to-one. So are there any questions about 11 through 16? All right. Find the inverse of a function. Are there any questions about how to find an inverse of a function? Okay, find inverse functions on limited domains. We need to go over 24 through 29.
Can we do 28?
28, sure. So f of x equals the quantity of x minus 2 squared, and then g of x equals radical x plus 2. They're inverse functions for what values of x? Okay. So when we are given a quadratic function, it will look something like this. And since it is not one-to-one, we know that there's only going to be an inverse on a limited domain. Usually we will take this section and we will only take the positive function of the square root of x. So for x minus 2 squared, we are going to have, we know that there's a shift. So we're going to have quadratic function like this with the vertex at x equals -2. Hold on. It'll be the positive direction. That's my bad. So we will have the vertex at x equals 2. And we know that this is the inverse, and it will look something like this. So we know that they are only inverses from x equals, so this is x equals 2. So it will only be inverses from 2 to infinity. Are there any questions about that?
Somebody also wanted to go over number 24.
24. So find the inverse of f of x equals 4x squared. So f of x equals 4x squared. 4x is greater than or equal to 0. So we can find the inverse of 4x squared. We will switch the x and y. Divide by the 4. And we're going to take the square root of both sides. So we know that the inverse is going to be the square root of x over 4. But we also have to look at the domain. And when we switch x and y, we know that we will be looking at when y is greater than or equal to 0. Are there any questions about that? Graph inverse functions. Do we have any questions about 26 through 30? Solve applications involving one-to-one and inverse functions. Do we have any questions about 32 through 34? Answer questions involving inverse function graphs. Do we have any questions about 38 through 52? All right, so that is the end of chapter 4.
We have somebody for 38.
38. Okay. So the model for body heat loss depends on the coefficient of convection K equals F of X, which depends on wind speed X. According to the equation, F of X equals 4 times the square root of 4X plus 1. What are the domain and range of this function without regard to the context of this application? Find the inverse of this function, and what are the domain and range of the inverse function? So what are the domain and range of this function? We're going to look at under the square root. We know that 4x plus 1 cannot be a negative number, which means that 4x plus 1 has to be greater than or equal to 0. And we can solve the domain solving that equation. And then for b, find the inverse of this function. So I'll write this out. So 4x plus 1 is greater than or equal to 0. For b, find the inverse of this function. Again, we will switch x and y. So we will have x equals 4 times square root of 4x plus 1, and then 4y plus 1. And then we're going to solve for y. So x over 4 equals the square root of 4y plus 1. And then we're going to square both sides to get rid of this square root. So we're going to have x squared over 16 equals 4y plus 1. So x squared over 16 minus 1 equals 4y. Then we're going to divide by 4 to get rid of that 4. So we're going to have x squared over 16 minus 1 over 4. And then we can simplify this and find our inverse. And then see what are the domain and range of this inverse function. And so you can find the domain and range either graphically or looking at it algebraically. Are there any questions about that? All right, so that will be the end of chapter 4. Next, we will be looking at chapter 5, and I'm going to hand it over to Stephen.
Awesome. Yeah, my name's Steven. I'm going to be going over chapter 5 with you all. So if we just get right into it, this is solving simplified expressions involving integer exponents. Any questions on this?
That's the toolbox, skip that.
Oh, skip that one. Oops.
Yep, no toolbox.
So skip all 1 through how many? Okay, so are there any questions on 11 through 24 then? There's that. Number 11.
and 12.
11 and 12, okay. So for number 11 here, we have x to the negative 1/2 times x to the 2/3. When we are dealing with exponents that have the same base, that are being multiplied together, so these are being multiplied, we can just add these exponents. So we'd end up getting x to the negative 1/2 plus 2/3, which we can just make sure they have common denominators. So that would be 6. So if we multiplied this one by 3/3 and this one by 2/2, we'd get x to the negative 3/6 plus 4/6. And that would be, we'd end up with x to the 1/6. And that would be our answer here. So anytime we have them multiplying by each other, we're just going to add those exponents.
We don't need to do 12 anymore.
And so, yeah. Yeah, any more questions on that section? Okay. Rationalizing the not rationalizing.
Go down to 31.
31.
That's where you start section 5.
Ah, I see. Haha. So now 5.1, identify exponential functions and distinguish between exponential growth and decay. Do we have any questions on 1 and 2? Yeah, sorry, keep flipping around, see how many we are. All right,
44.
44. Do you want me to go over out
Is
for
that still-
toolbox? For
Somebody
44.
asked for 44.
Yeah, go ahead, that's fine.
All right, so for number 44, it's using scientific notation to show us that fraction. So scientific notation, we're just changing that many decimal places. So for 2.91961 times 10 to the negative 2, we're just going to move that decimal point 2 points to the left. So we'll be at 1, 2. And that would have a 0 there. So we'd have 0.02961. And then we'd also have, the next one was to the 4. So 4.583 times 10 to the negative 4, which would be 1, 2, 3, 4. So we'd have 3 zeros there. 0.0004583, and it wants us to write the result in scientific notation. Not sure if I know how to do that in my head.
No, you can't do that in your head.
So
You could probably divide the two numbers and then divide the 10 to the negative 2 over 10 to the negative 4.
yeah.
That's just plug it in your calculator and solve and make sure it fits.
Yeah. Plug in your calculator and you may get something that says like 2.827 or 872 e to the 4 or e to the negative 4. All that is doing in your calculator is the e is just acting as scientific notation. So that e acts as 2.872 times 10 to the negative 4. That's all that is. So you're just moving that decimal place. Awesome.
So somebody said we need to go over the rules for growth and decay.
The rules for growth and decay, which are, sorry, right there. So the rules for growth or decay, for an exponential function, that means we have an x in our exponent. So if we read this little box here, or I guess that just defines an exponential function. So looking at number 2, if we look at number 2, and we have 2 to 0.01x, we know that for every x here, this number is only going to get smaller. So we're going to have less and less and less of 2. So for this one, since our base is larger than 1, so our base is larger than 1, and our exponent up here is less than 1, it is going to be a decay function. So our base and then our exponent is less than 1. That is going to be a decay. Now, if we look at D, where we have 0.8 to the 3x, our base is less than 1, but our exponent is greater than 1. So that 0.8 is just going to multiply by itself more and more and more. And so we're also going to have a decay function. So if our base is greater than 1 or exponent is less than 1, it's going to be a decay. If our base is less than 1 or exponent is greater than 1, it'll also be a decay. Now, anytime we have a negative in our exponent and our base is greater than 1, it's still going to be the same thing, right? Because that exponent is still less than 1. We will have growth when our base is greater than 1 and our exponent is also greater than 1. Otherwise, it will be decay. That answer the question.
So if either one is less than 1, it's gonna decay.
So if the base is less than 1,
If either the base or the exponent are less than 1, it's gonna decay.
one or the other is less than
If
1.
you flip to page 35 under the notes, I've got the exponential growth and decay models there, and it summarizes all of that.
Yeah, so that these parts talk about what A, K, and what A and B can be. Yeah, it's kind of complicated, but when worse comes to worse, also remember you have your calculator to graph it. And if it's going down, it's decay, and if it's going up, it's growth.
Okay.
Next section, graph exponential functions by plotting points or using a calculator. Any questions on 3 through 12? Next one is use transformations to match a graph with its equation. So 13 through 16. These are all of our transformations from previous, just applied to a different function. Use transformations to graph the exponential functions. What about 19 through 34? Solve applications involving exponential functions. So 35 through 54. All right. 5.2, logarithmic functions. So I'm just gonna have to convert logarithmic expressions to exponential form. So 1 through 4.
We do 3.
Number 3. So just that blank. Awesome. Number 3. Number 3 says the ln of 2x. Well, our ln is just our log, our normal log, to the base of e. So log base e of 2x. And our logarithms want to know e to what exponent is equal to 2x. So e to, I guess, yeah, e to the y, right? E to the y is equal to 2x. And that's how we would rewrite that logarithmic equation. So our ln's are just log base e. So e is always, the base is always our base, and then the exponent's over there. Does that make sense?
Number 2.
Number 2. I think I have room on this notepad. So number 2, log base 5 of x is equal to 2y. So we know 5 is our base down here, So we can always start with that. So we have 5 to the 2y, because logarithms want to tell us what our exponent is. 5 to the 2y is equal to what's on the inside of the logarithm, which is x. It's just kind of one of those things you got to remember where everything goes. The base stays at the base of the exponent. The logarithm is the what's inside the logarithm is the answer. And then our answer is our exponent. Awesome. What about converting exponential expressions to logarithmic form? So 5 through 8, doing that backwards.
Could do 8.
Number 8, okay. So we have 9 to the 2x equals y. So we know we can always start with 9 is going to be our base. So log base 9 of, well, y is our answer over here. So of y is equal to that exponent up there, to the 2x. Our exponent is going to be what the logarithm wants to know.
7.
7. These are kind of getting scattered. Make it a little C note. Why are they so large? Okay. Number 7. And I scroll away. 32 is equal to 2 to the 5th. Rewrite that as a logarithm. So 2 is the base of our exponent. So we have log base 2 of 32, because that's our answer over here. 32 is equal to 5. So our exponent is our answer, and our answer is what's inside the logarithm. So awesome. What about exercises 9 through 13, evaluating logarithms? All right. Graph and analyze logarithmic functions. So 14 through 18.
Do 18.
Number 18. So we have, let's see, this. 18, right? So we have y is equal to ln of x minus 2 minus 3. So our normal graph of the natural log is just going to look something like that, right? We can see that down here in A. We can see our graph, since it's positive, is going to be something like that. But now, like we were doing earlier, we can apply our transformations. Well, we know that x minus 2 is in the parentheses here. So we're going to move this to the right 2. And then we have this minus 3 on the outside. So we're going to move it down 3. So we're shifting it to the right 2 and down 3. Which, so when we went to go graph that, it would come out to the right over here. So at 2, it'd come out here, and then it'd also shift down 1, 2, 3. So it looks something like that. Any more questions on those? Awesome. Find and graph the inverse of exponential functions. Okay. Rewrite logarithmic expressions using properties of logarithms. So 31 through 38.
You do 33.
33?
We have 32.
33 and 32. Awesome. So we want to rewrite each expression as a sum, difference, or product of logarithms. So in 33, we have log base 3 of the cube root of 4x plus 1 over 4x squared. So we know that anytime we have division between logarithms, we can change it to subtraction. So that can be our first step. So we have log base 3 of the cube root 4x plus 1 minus, because that was on top, log base 3, our bases will always stay the same, of 4x squared. Okay. So now what else can we do? Well, we know that the square root of, or the cube root of 4x plus 1 is the same thing as writing 4x plus 1 to the 1/3. And we also know that 4x squared is the same as writing 2x squared. And using our rules of exponents within logarithms, we can bring those exponents out to the front and multiply. So we'd have 1/3 log base 3 of 4x plus 1 minus, we bring that 2 out front, log 2 log base 3 of 2x. Which if we want, we can keep going as well. Because we know, I don't know how far it's going to want us to go, but we know this is just 2 times x here. So we could rewrite that as log of 2 plus log of x. But I think leaving it right here is where we should stop, because that would leave us with x's in our logarithm where we want them. How's that? Does that help? Do you still want me to go over 32 or? For the sake of time, should we move on?
Yes.
All right. If we have time, we'll come back for 32. Solve applications using logarithms. So 39 through 70. 5.3, exponential and logarithmic equations. So solve the exponential equations, 1 through 10. How do we feel about those? Any questions on those?
Should we just do like 5?
Number 5. All right. We have large sticky note. That's what we have. All right. Number 5. Oh, I did not. 5 says 8,900 is equal to e to the 5x. So on a lot of these, we're going to use our calculator to help us solve, especially when we need to take logarithms. So to get our x out of the exponent, we can always use the natural log. So if we took the natural log of both sides, so we'd have ln of 8,900 is equal to ln of e to the 5x. Well, we know our exponent rules say that we can bring that 5x up front. So we'd have ln of 8,900 is equal to 5x times ln of e. Well, that's just log base e of e. Anytime the base is to itself, it's just going to equal 1. So ln of E is equal to 1. So we just have ln of 8,900 is equal to 5x, which we can divide 5 on both sides. So x is equal to ln of 8,900 divided by 5, which is equal to, we did it in our calculator, 1.81 thing, and it says round to 3 decimal places. So we do 1.819. That would be our answer.
Also number 10.
And number 10 as well. So we have number 10. 9,000 is equal to 400 times 10 to the x. Well, like in any other algebra problem, we need to get x by itself before we can start messing with what's touching it. So first we'll start by dividing by 400 on both sides. So we'll have 90 over 4 is equal to 10x. And we can just rewrite that as a logarithm, right? So we have our base, we have our log base 10 is of this 90 over 4 is equal to x, right? Because our logarithms just tell us what the exponent is. So we can just plug that in. So if we did log, and on your calculator, the log button defaults to log base 10. So we have log of 90 divided by 4. And that gives us x is about, or x is equal to 1.352. Any questions there? All right. How about 11 through 14 using the change of base formula?
You just took 11.
Yeah. I'm going to move number 10 up here. That way we can see what our change of base formula is. So number 11, right? We have log base 6 of 18. And we want to use the change of base formula to to evaluate each logarithm. So, I don't know what I did. So, I don't know what we want to change our base to. What do we want to change our base to here?
What question is it?
Number 11. Oh, well, that wouldn't really help either. What if we change it to base 18? Think that's what it wants? Because if we had log base 18 of 18, it would just be 1. Because we could just plug this in our calculator, all fine and dandy. But if we wanted to change a base, if we change it to 18, we do log base base 6 of 18 over oh no, log, okay, sorry, having a mind fart. We're having log base 18 of what's inside. So this b is our base that we want to change to. Log base 18 of 18 over our log base 18 of 6, which doesn't really help us a lot. However, yeah, I'm not sure what base it would want us to take it to. Using change of base formula it's helpful when we are given 2 different bases. So if we had 2 different logarithms here, so we had log base 6 of 18 plus log base 7 of 215. if we wanted to change one of those to log base 6, that way we could add them. That's where our change of base would all come in handy a bit more. Because we could just plug these into our calculator pretty efficiently. Any questions on that? I know I did a pretty rough job of explaining it, but our formula is right here in our notes.
All right, we've got about 10 minutes remaining. So if we want to open it up to any questions you might have, pages 44 through 55, we can take those at this time.
So we have solving logarithmic equations, solving exponentials, applications of those, using models to give logarithmic and exponential equations, determining if they're exponential or not, applications again, and then answering with exponential growth, and then loan repayment. And that, I believe, concludes us. So any questions over any of those pages?
We do 18 on 44.
18 on 44. All right. So that is this one right here. So 18, so we have 2 times 6 to the 2x is equal to 200 or 2,592. So similar to the one we did earlier, we need to get this 6 to the 2x by itself first. So we're going to have to divide by that 2 on both sides, which gives us 6 to the 2x is equal to 1,296. And now we can rewrite that as a logarithm, whether if we want to use the LNs, which is our change of base, or if we just want to rewrite that as a logarithm. But I'm going to use the LN method for, what's the word I'm looking for? Consistency. So if we took the LN of both of these sides, so we have LN of each side, we can use our exponent rule to bring that 2x up front. So we have 2x times ln of 6 is equal to ln of 1296. To get that x by itself, we divide the ln of 6 on both sides. So that number is kind of gross. So we'll just write 2x is equal to ln of 1296 over ln of 6. So we can just divide by 2 on both sides to get x by itself. X is equal to ln of 1296 over 2 times ln of 6. And we can just plug that in. So I believe.
I got 2.
Yeah, is it really that nice?
Yeah. And I did it using log base 10 just for funsies.
Oh, did you?
Yeah.
And so x is equal to 2.
All right, what other questions do you all have? I know it gets pretty intense towards the end here with the logs and the exponents.
I hate logs.
I feel you.
So I'm doing this section.
Yeah.
I like logarithms. Logarithms just want to tell us our base to what exponent. We want to find exponents when we're dealing with logarithm. And that's why we pair both exponential equations and logarithms together.
So like, I'm just gonna try 16. So it would go log 9 base. Then the number would be 2187. And then equals x.
Perfect.
Can we go over number 15 on 54?
Number 15 on page what?
54.
Number, which one?
15.
15, okay. find the present value of an annuity that will pay $1,000 at the end of each year for 10 years if the interest rate is $7,000 compounded annually. So we know that R is to be made at the end of each pay period. So that's how much we're going to pay at the end of each pay period. So we're going to pay $1,000 at the end of each pay period. So R is 1,000. We know that we have N periods from an account. So how many periods? We have, I believe, 10 periods. So that would be N is equal to 10. And then we have earns an interest rate at I per period. So 7% per year, right? So annually per year. So we have I is equal to 0.07 a year. Now, we know all these, so we can just plug them into this formula we're given down here. We have A is equal to R, which is 1,000, times 1 minus 1 plus I, which is 0.07, so 1.07, to the negative 10 all over 0.07. And that's, I would plug into your calculator. 1,000. Negative 10. And I believe you all should get a formula sheet for this. Is that true? Do you know?
I don't know that.
I believe you will get a formula sheet. Don't quote me on it though.
All right, so the 3 minutes we have remaining, are there any other questions you'd like to see?
I believe there were some questions that we didn't get to earlier. Do you guys still want to go back and look at those?
I think they're worn out.
It's a lot of math.
So
It's
am
a ton of
I.
math. All right, well, I just want to thank everyone for coming and hanging out with us tonight and geeking out over some math, whether it's logs, exponents, formulas, you name it. If there's anything we can do to help you out in preparing for your midterm, please let us know. Otherwise, I've got everybody's email addresses captured. As soon as this video processes, I will send out both the handwritten notes that we took and the YouTube video of our lesson tonight. All right, thank you all so much.
If you guys have any more questions, feel free to stop by the tutoring center and we can do more one-on-one help if you have any more questions.
Oh, we got this book.